So in this video, we're going to introduce the idea of trigonometric substitution. We just want to kind of go over the key concept, and then in subsequent videos we'll show applications of this concept. So when you're doing trigonometric substitution, there's two things that you want to do. The first thing, and most importantly, is you want to make sure there isn't a simpler method to evaluate the integral. If you can come up with an easier way to do it, you want to do it the easier way. But if you're stuck, then trigonometric substitution might be a tool that you can try to apply. The key for using trigonometric substitution is you're looking for the Pythagorean theorem to be showing up in the integral that you're working with. So here's the idea. The Pythagorean theorem, if we have a right triangle, the Pythagorean theorem says that if you have the hypotenuse and leg 1 and leg 2, we know that the square of the hypotenuse equals the sum of the squares of the right triangle legs. And we could solve this for, that should be leg sub 2. We could solve this for either one of the two legs if we wanted to. So for example, we could identify that the leg 1 squared is equal to the hypotenuse squared minus leg sub 2 squared by algebraic manipulation. So this is really what you're looking for. You're looking for, in trigonometric substitution, either a sum or difference of squares showing up in the equation, which identifies to you that you might be able to convert from rectangular form into a trigonometric form. So for example, if we had 1 plus x squared showing up in the integral, maybe under a square root sign, maybe not. But if we did see 1 plus x squared, we recognize there's a sum of two squares. And if we have a sum of two squares, we might be able to represent the elements that are being squared as leg lengths on a right triangle. So for example, if I drew in another really horrible right triangle and I labeled this angle theta, I might be able to say, for example, maybe this has length 1, this height is height x, and if we did that, the Pythagorean theorem would tell us that the length of the hypotenuse would be the square root of the sum of the squares of those two legs. And then we could take and convert from rectangular world, 1 plus x squared, into trigonometric world by recognizing that the cosine of theta would be equal to 1 over the hypotenuse from our trigonometric definitions, so 1 plus x squared. If we needed to, we could identify the sine of theta, which would be the side opposite theta, x over the square root of 1 plus x squared. We could get the tangent of theta, for example, by doing x over 1, which is just x. And we could also come up with the secant, cosecant, and cotangent. So we convert from rectangular world into trigonometric world, and the idea is we want to try to convert the integral from rectangular world into trigonometric world, and then we want to identify whether any of the tools and techniques we've developed for evaluating trigonometric intervals can be applied to resolve the integral. The Pythagorean theorem doesn't have to be showing up in an explicit way. So for example, if I had 2 minus x, this could still be written in a way that is conducive to the Pythagorean theorem, because we could write this as the square root of 2 squared minus the square root of x squared. And then I could walk through and label a right triangle with that information. I would notice that I have a difference of squares. So I have theta. The thing that comes first, the thing that isn't being subtracted, has to be the hypotenuse. So I would put the square root then into the hypotenuse position, and that would make this other one of the two legs. So the square root of x I could either put here or here. It would be my choice. So for example, if I wanted to make the side opposite the square root of x, then this leg would just be the square root of this stuff here. The square root of this stuff would be the length of the other leg. Just like here, we had the difference of squares. So if I wanted to know the length of leg 1, I would take the square root of both sides to get that. So this leg right here would be the square root of 2 squared minus the square root of x squared, which is just the square root of 2 minus x. And then I could convert again into into trigonometric world using the definitions of the cosine, sine, tangent, secant, cosecant, cotangent functions. So that's the basic idea behind trig substitution, and now we'll walk through a series of videos where we apply trig substitution to resolve some integrals.